Anybody have any questions? Oh, so as far as the exam, those will definitely be graded Wednesday, but I don't have them yet. Anybody have any questions about what we've been talking about? Anyone remember what we've been talking about? This is probably worth thinking about for a second. So we were talking about internal loads. We're going to keep talking about internal loads. And it's such a big detour that I think it's easy to lose track of why we're talking about it now. So what's the big picture? Like, why are we talking about internal loads right now? What? Yep, that's exactly right. Because so far we've talked about how to calculate stress and strain if you have uniaxial tension or compression. Now we have to talk about how to calculate stress and strain if you have shear forces and bending moments. But before we can do that, we have to make sure everybody knows how to figure out what the shear forces and bending moments are. You know, calculating tension and compression is sort of automatic. You know, it's like super easy, but there's a little more to calculating shear forces and bending moments. So that's what we're doing on the way to calculating stresses and strains. And so last time we did it with point forces. We talked about how to calculate internal loads on something that has point forces. Now I'm going to talk about internal loads. Oh yeah, let's do that. Internal loads in the presence of distributed loads. Yeah?
How did they figure out that the easiest way to analyze a point is through a cube? Why can't it be like a sphere? Or, is a cube the easiest way to analyze a point?
It's not really a cube. It's the fact that you have that on a, so think of every axis representing a plane. Okay, there's, you know, like from math, there's always a relationship between a normal vector and a plane, right? And so think of every axis as being the normal vector to a plane. On each one of those planes, there's a vector of stress elements, okay? And so the cube is just, so that gives you those 18 values. Half of them are equal and opposite to the other one. So that gives you those 9 values of the stress tensor, okay? And the cube is just a way to draw that relationship between normal planes and vectors, I think, is the answer. So you need those 9 values, and a sphere wouldn't let you represent it, you know. I mean, if you used a sphere to do it, you'd be representing it the same way, but it just wouldn't be as visually clear, you know. So I think that's why. It's because of the number of values you need to represent the stress. Any other questions? Okay. So as far as distributed loads, sometimes, and really probably always, but forces are spread out over some area. So for example, something that, you know, before maybe we've been representing this way, where you have this member and a single point force like that. For more detail, you might want to represent like what it really is, say, is the same force F, but spread over some small, in 3D it would be an area, in 2D it would be a length L. So say it's still this force F represented over L. And in engineering problems, the way you show that is with this distributed load like this, and the height or the magnitude of that distributed load is given as the total force divided by the length in units of force over length. Like, for example, we're going to always be doing it in newtons per meter. The most important source of distributed loads is weight, whether it's the weight of the object you're dealing with or another object that's pressing down on the object, your chosen object. So most of the time when we deal with distributed loads, it's going to be because of object weight. So until now, or we've usually treated weight as a point force. Acting at the object's centroid. So for example, if you have an object like this, we've treated the weight as a force vector pointing down from the centroid with a magnitude of mg. But it's really this. So you have an object like this. The weight is a uniform distributed load. And if the length here is capital L, then this distributed load has a magnitude of the total weight divided by L. In force per length, units of force per length. So is this something we've been doing as an approximation up until now? Or is this something that has been okay up until now, hasn't changed answers, and for some reason now it's going to change the answers? What do you think about that? It's what? This one? Yeah, right. So this is what's really happening with the weight, but we haven't tended to treat problems that way. So I'm asking, like, what's your intuition about the way we have been treating it? Do you think there's something about those problems that make this equivalent to this? Yeah, or that's what it is. And then my other question was, or is there something new that's going to happen that's going to make us all of a sudden have to go from talking about weight this way to talking about weight this way? And the answer is yes. Everything that we've done up until, the answer is yes. Up until now, everything we've done is perfectly, correctly treated this way. But now we're about to hit a topic where we have to deal with this, okay? We have to deal with the fact that weight is actually a distributed load. So until now, treating the weight as a point force hasn't changed answers. Now with distributed, or with, now with internal loads, calculating internal loads, it does make a difference. And so the reason that it makes a difference is so that difference comes about for the following reason. So it occurs because you can't treat a distributed load as a point force until you've chosen the body to isolate. Once you've chosen your free body, then you can. So you can treat a distributed load as the equivalent point force. Okay, so most of the class today, I'm going to do these two problems. I'm going to do a simple, like a statics problem for a beam that's simply supported. And I'm going to show why treating it as a distributed load gives you the exact same information, values, answers, as treating it as a point force. And then I'm going to do a simple internal loads problem. We're going to do it treating it as a point force. We're going to do it treating it as a distributed load. And hopefully you'll just sort of see where that jump has to be made between going from a distributed load to the equivalent point force. Okay, so once you choose, okay, so how do you treat a distributed load
easily be teaching a class on how to kill people. Pick a point, exert force.
Yeah.
Isolate the body.
Well, I mean, I assume that's what most of you, not all of you, but most of you after you graduate, that's what you'll be doing with this. Okay, so how do you treat a distributed load as an equivalent point force? So first, the magnitude of the equivalent point force is the area of the distributed load. So as an example, if you have a distributed load of 10,000 newtons per meter and a length of 3 meters, then just think of the rectangle of the distributed load. Obviously, it's not drawn to scale, and it's going to be in funny units compared to most area calculations you do, but you can think of the height as being 10,000 newtons per meter, the width as being 3 meters, and so you end up with a total force of 10,000 newtons per meter times 3 meters, so 30,000. And what units do you get? Hey, that's awesome! Because that's what we want. And then second, what's the second thing you have to know about this equivalent point force? Where it is, and why do you have to know that? Yeah, right, it's going to change what moment it produces, yep. So the location of the equivalent point force is the centroid of the shape. So, for example, if we have that shape we just had a minute ago, the height here is 10,000 newtons per meter. The width is 3 meters. What's the centroid of that distributed shape? Well, what is the distributed shape? A triangle? Right, rectangle, the 4 one, the one with 4. Where's the centroid of the rectangle and why? Yeah, it's right in the middle because of the symmetry thing. The centroid has to lie on any line of symmetry. And so the centroid here is where those 2 lines of symmetry cross. So this is 1.5. We don't know the height here. In this case, it won't matter because, so if I draw this, we end up with a force of 30,000, let's see, 30,000 newtons. Oh, we do know the height, you're right. Yeah, so this would be, thank you. This would be 5,000. And this distance is 1.5 meters. We do know the height, but it doesn't matter what the height is. And the reason it doesn't matter is because this is a vertical distributed load. And remember, you can always move any point force anywhere along its line of action without changing the behavior. So you can move this up and down. It doesn't change anything about your calculations. Okay, so this is easy for these uniform distributed loads, these rectangular distributed loads. And a little later on, I'll talk about some other simple shapes. This is the easiest one. And the nice thing is when you're talking about a beam that has a uniform thickness, you know, it has the same cross section all the way along, the distributed load is always a uniform distributed load. Okay, the weight is. Okay. So now I want to do an example. So I'm going to start out with this sort of basic beam problem. Let's say that the length of the beam is 2 meters and the mass is 1,000 kilograms. And I want you to solve first, assuming, well, by solve, I guess, the first example we're going to do is solve for the reactions. Assuming that the weight is concentrated at the centroid. And second, assuming that it is a uniform distributed load. And what's going to happen in this example problem? Yeah, they're going to be the same. So first, I'm going to do it as this problem. Where this force is 98.10. Free body diagram. We have a force vector here. A force with a known direction here. A downward force of 98.10. So Newton's second law says RAX, RAY plus 0, negative 98.10 plus 0 RB is equal to zeros. In the rotational equation, I'll calculate the moments about A. So we have minus 98.10 plus 2RB is equal to 0. So RB is equal to 4905 and RA is equal to 0.4905. And so now let's go to the second one, and we're going to assume in this case that this is a distributed load. So what would be what's the value of this uniform distributed load that would appear here in a problem to make it equivalent to, I mean, this whole distributed load adds up to the weight of the beam, right? I mean, adds up to the weight of the beam. So it has to add up to 98.10. So how would we turn that into a distributed load? Yeah, just divide by the length. Yep. And so we'll represent this as 4905 newtons per meter. Free body diagram. we have a force vector there, an upward force there, and a distributed force here. But now that we've chosen the free body, to solve, we treat the distributed load as a point force. So now we take this free body, treat this entire distributed load as a point force, and it simplifies to this beam with the force RA, the force RB, and a downward 9810. Okay. This is exactly the problem that we started with in part A. So we're going to get the same reactions. Okay, so now any questions about that? It's 2 meters long. Did I not say that? It's 2 meters long. The distributed load, though, is 4905 because any other questions? Okay. So now I'm going to do the same thing, but I'm going to do internal loads, and we're going to see that it doesn't come out the same. So why don't, we're going to do the same body. Where this is 2 meters. The mass is 1,000 kilograms. You're going to solve the internal loads, so the tension, the shear force, and the bending moment. First, assuming that the weight is concentrated at the centroid. And second, assuming the weight acts as a uniform distributed load. Okay, so for part A, the problem is this. And we've already calculated those reactions, so I'm not going to do that again. So free body diagram of the whole thing, we know that we have, well, we can whoops, we have a force of 4905 here, a force of 4905 here, and a downward force of 9810. If we're going to calculate the internal loads, how many important points are there? 3. So how many cuts do we have to make? 2. Yep. So we have to make one cut where the right end of the cut is going to represent something between 0 and 1 meter, and a second cut where the right end represents anything between 1 meter and 2 meters. So the x values that we're calculating for the first cut are 0 to 1. And so a free body diagram of this cut looks something like 4905 up. And then what other loads are acting on this? We know the right end hasn't gotten to, even the biggest it can be, it hasn't quite gotten to that, to where that weight is acting. And so the only other loads are the tension, shear force, and bending moment. And so Newton's laws say 0, 4905 plus T0 plus 0 negative V is equal to 0. So there's no tension. The shear force is equal to 4905. And then the moment equation, the about point is at the left end. So the 4905 force doesn't produce any moment. The couple produces a moment. And then the shear force produces a clockwise moment with a moment arm. If this thing is represented by the length x, then that shear force produces a moment of v times x clockwise, so minus vx. That's equal to 0. So the bending moment is positive vx, and v is 4905, so that's 4905x. And now cut 2. We're going to represent the x values between 1 and 2. We always go all the way from the left, so we always have this 4905. What other loads are acting here? What? The weight is on this one, yep. So 9810. And then the internal loads. So Newton's second law says 0, 4905 plus 0, negative 9810 plus, I'm going to combine the t and v into one vector. Just add them together and you get a vector like that, is equal to zeros. And so you get that the tension is still 0, but the shear force now, instead of up here it was positive 4905, now it's equal to negative 4905. And the moment equation, we have a clockwise moment of 9810 times 1, so negative 9810 plus m minus Vx is equal to 0. And so the bending moment is equal to Vx plus 9810. So negative 4905x plus 9810. And if you graph these, the tension is 0 all the way across. The shear force, whoops, the x-axis should be x. The shear force for the first half is positive 4905. And for the second half is negative 4905. And the bending moment looks like that. And I guess this value is 4905. Okay, so what are the sanity checks? Let's just make sure that we got these right. What can we do looking at this to make sure that it makes sense? Okay, yep, so the first one is dm dx is equal to v, check. Okay, that works out. What are the other ones? What should we? That's right. So there are no point couples at either of the two endpoints. So the bending moment should be 0 at the two endpoints. Oops. At ends, because there's no point couples at the ends. Okay, so that one works. There are two more.
There are point forces at the endpoint, so we do expect.
And we can actually even break that up into horizontal versus vertical ones. The tension should be equal to 0 at the ends because there's no point horizontal forces. And V, we can't really say anything about. It's not equal to 0 at the ends, but there are vertical point forces. Okay, so this checks out on all four of those. All right, so let's now do the problem with distributed loads and compare the diagrams that we get to these. So now we're going to do the problem this way. The distributed load is 4905 newtons per meter. We know those reaction forces. We already calculated those. We have this one up at 4905, this one up at 4905, and then that distributed load. How many important points do we have in this problem? Just two, because the ends are the only place that that distributed load function changes. So the only two are the endpoints, which means we only have to make one cut. So cut 1. This is going to represent all the x values between 0 and 2. And so to draw the free body diagram, we have 4905. We have this distributed load. We don't have this other 4905 because whatever the length of this thing is, and we're going to call it x, it's not ever going to be all the way out at 2. And so the only other forces acting are tension, shear force, and bending moment. Okay, so to solve this now, now that we've chosen the free body, we're going to treat the distributed load as a point force. But notice that now that we've chosen this free body, and this free body doesn't have, it's not the original body in the problem. It's not the full beam. That centroid is not going to, it's not going to be at 1 meter, okay? That centroid is going to be at the centroid of whatever this is. It's going to depend on the x value. If x was small, if x was 0.1 meters, then the centroid would be 0.05 meters. It'd be really close to the left. If this was close to 1.9 meters, the centroid of the distributed load would be 0.95 meters. So its location moves depending on what x is. And so when I treat it as a point force, both the location of that point force and the magnitude of that point force are going to be functions of x. They're going to depend on x. Okay? So, yeah.
Just the summation of the x length for the.
Say it again.
The summation of depend on the x.
Yeah, when we turn this into a point force, you can imagine with this distributed load, if in the case where x represented a very small value, the magnitude of the distributed load would be very small, You'd have, so say this distance was 0.1, and your distributed load here was 4905 newtons per meter. Then the total area of that shape is 490.5. It's a small total force. If this was bigger, like 1.5 meters, the total force would be bigger. And so how big it is depends on what x is. And so it's going to have to appear as a function of x. Okay, so we know that this force is going to act at the centroid of the shape. If the whole shape has a length of x, then the centroid here has a length of x over 2. And what about the area? The area of this shape, the magnitude of that force, is going to be 4905 times x, right? So this point force is going to be 4905x. And now we have T, V, and M. Newton's second law says 0, 4905 plus 0, negative 4905x plus t negative v is equal to zeros. So t is equal to 0, v is equal to negative 4905x plus 4905. And then the rotational equation. This point force produces a clockwise moment with a magnitude of 4905x times its moment arm of x over 2. So we have negative 4905x times x over 2 plus the couple minus Vx is equal to 0. So m is equal to positive 24, what is it? X plus Vx, so 2452.5x. Yeah, thanks. Plus negative 4905x plus 4905 times x. So 2452.5x squared minus 4905x squared plus 4905x. And so the final function you get is negative 2452.5x squared plus 4905x. And so the graphs you get look like this. For the tension, you still get 0. For the shear force, you get a line that goes from positive 4905 to negative 4905. And for the bending moment, you get something like that. And if you compare these shapes to the shapes we got the other way, like notice that they do have something in common. In a way, you can think of treating it as a point force, treating the weight as a point force as a way to roughly approximate the shapes that you get, doing it accurately. And you can imagine a scheme where you treated it as a bunch of point forces and got closer and closer as you treated it by more point forces. But this is why with distributed loads, you have to treat weights as distributed loads. With internal load calculations, you have to treat weights as distributed loads. Okay. Okay.